In this video, we're going to continue our discussion of interest, but we're going to expand our formulas to deal with situations where we're not keeping the amount of principal in an account constant. So we've looked at three formulas so far. We've looked at a formula for calculating simple interest, and then we've looked at formulas for calculating periodic compounded interest, and then continuously compounded interest. But what's specific to those formulas is the fact that the principal is considered to be a fixed amount. So any changes to an account represent interest that's being accrued on that account. So what we want to talk about now is what happens when the amount of principal is not constant. What if we're actually continually adding our own money to the account? If that's the case, then those particular formulas are not going to be able to handle big picture issues in terms of calculating the balance in the account. We could use each of those formulas individually every time we add a new amount of principal to the account, but unless we want to have to do individual calculations every single time we add money to the account, those formulas just aren't going to cut it. So we are, again, a little bit limited as to the situations we can deal with. We have to have specific kinds of additions of money to the account. So what we're going to focus on is what we call an annuity. So an annuity is a sequence of equal periodic payments. In other words, the amount being deposited in the account, the amount of principal being added to the account, is going to be a fixed amount. Every single deposit into the account is going to be a deposit of the same amount. And then also deposits have to be made at equal intervals. So suppose we make monthly deposits. Well, we have to assume that every single deposit is made into the account at the same time of the month, and then at the same time of the next month, we make the same deposit again. So this does, again, limit us in terms of specific situations that we can handle. This is, again, kind of an oversimplified version of different things that can happen. So if you're just periodically adding money to your account and it's never a set amount, there isn't really a formula that can be used to handle that kind of situation. In that case, you would just have to manually calculate your account balance using the basic interest formulas every time you added money to the account. But the idea here is that if we're keeping things constant in terms of how much we're putting into the account and how frequently we're putting things into the account, then we have formulas that can handle those kinds of situations and can tell us what happens in the long run based on making those kinds of deposits. So this idea of an annuity, equal periodic payments, we have two versions of what an annuity can look like. So if payments are made at the end of the period, in other words, like the end of the month, then it's what we call an ordinary annuity. Whereas if payments are made at the beginning of the month, then it's what we call an annuity due. And it says we'll only consider the second type. It should say the first type. So we're just going to look at ordinary annuities. The formulas for either one are pretty close, but just for consistency's sake, we're going to focus on one kind of formula, one kind of annuity. So specifically situations where we're making deposits into an account at the end of whatever period we're looking at. Now, what we're going to focus on in this section is what we call the future value of the annuity. So the future value of this sequence of payments is going to be the sum of all the payments that we make and then all of the interest that is accrued on those payments. So the reason we call it the future value is because it represents what the account will be worth in the future once all of the payments have been made and once we've collected all the interest that we're owed on this account. Now, why can't we just use an interest formula? We know how much money we're putting into the account. We know how long we're going to keep the account, so why can't we just use the standard compound interest formula? Well, the reason we can't just use the basic formulas that we've already looked at is because we have to consider differences in time. So specifically, earlier payments, earlier amounts that we deposit into the account end up accruing more interest because they are in the account longer. So the more time the money sits in the account, the more time it has to collect interest. So ultimately, the more it's worth in the future. Whereas payments that are made later, closer to the end of what we're counting for for purposes of calculating the balance of the account. Payments that are made later have less time to accrue interest. So in the future, they're not worth as much as those earlier payments that sat in the account for longer. So each individual addition, each individual deposit into the account ends up being worth a different amount in the future, just because they all sit in the account for different periods of time. So let's look at a basic situation. I want to think through sort of the mechanics of what's happening. We're going to look at this in a very drawn out way, and then we'll talk about how you would simplify the situation and how you would use a formula to do some of this heavy lifting for you. So here's the setup. We decide to deposit $100 every 6 months into an account that pays 6% interest compounded semi-annually. So if we make 6 deposits, one at the end of each interest payment period over 3 years, we want to know how much money will be in the account after the last deposit is made. Okay, so why is this considered to be an annuity? Well, notice we're depositing a specific amount, but we're depositing it every 6 months. So in other words, think of it like a payment plan. It's a deposit plan. It's always going to be a deposit of $100, and every 6 months, we're going to make that same deposit at the end of the 6-month period. So because we're always depositing the same amount, and because we're always depositing it at the same time over equal intervals, this is what we call an annuity. Now, the reason it's an ordinary annuity is because we're depositing it at the end of the period. So anything deposited at the end of the period is what we call an ordinary annuity. Now, this particular account where we're depositing these $100 payments is subject to compound interest. So it's 6% interest, and it's compounded semi-annually. Now, one thing I want to emphasize here, notice that we're depositing things every 6 months, and we're also compounding the interest semi-annually, which also means every 6 months. These two values are going to have to be the same. So for all the situations we look at, how frequently we deposit money in the account and how frequently we calculate interest, those values have to be the same. So essentially the assumption we're making is that while we're depositing money, we're also accruing interest on whatever was already in the account. So we don't get to accrue interest on the new deposit, but we do accrue interest at the same time on anything that was already in the account. But those two values are going to have to be the same for any of the situations that we look at. So we're going to assume that we're making 6 deposits like this. So every 6 months, which means 2 per year. And then since we want to make a total of 6 deposits, that's going to take us to 3 years. So 2 deposits a year for 3 years totals up to 6 equal $100 deposits in total. Well, we can immediately identify how much money will be in the account based on how much we've deposited. So if we make 6 deposits of $100, assuming we start with a balance of 0, then that means there will be at least $600 in the account. Now that's $600 that just came from our money. We can think of that $600 as representing principal. It's just principal that was deposited at different times. We didn't deposit $600 up front. We spread it out into 6 payments and we deposited it over time. But what we're going to find is that at the end of 3 years, we're going to have more than $600 in the account. And that's because we have interest that's compounded semi-annually. So because we're accruing interest, we're actually making additional money on each one of those $100 deposits. The earlier deposit will be worth more, whereas the last deposit we make will only be worth a certain amount. So the longer the money spends just sitting there in the account, the longer it has to accrue interest, and the more it'll ultimately be worth once we reinvestigate the value of the account at the end of 3 years. So essentially what's going to happen is we're going to use the compound interest formula, but we have to use it individually every single time we make a change to the account. Okay. So here's our compound interest formula. Remember, this is the formula we used last section when we looked at periodically compounded interest. So P stands for principal, I is going to be our interest rate per period. We define that as the annual rate divided by how many times we accrue interest per year. And then our exponent N, that's going to be the total number of times we accrue interest. So in this case, if it's twice a year, semi-annually, for 3 years, then that's going to be a total of 6. So our exponent here is going to be 6 in total if we were to look at all the periods that we have to accrue interest. So let's start with the rate per period. Whenever we look at a situation with an annuity, we want to start by determining what that rate per period is, because knowing that up front is going to make some of the formulas a little bit easier to use. So our interest rate is going to be 6%, which is 0.06, but the interest is compounded semi-annually. So we don't get 6% every time. We use half of that percentage, but we use it twice a year. So 0.06 divided into 2 parts, because the year is dividing into 2 parts, and that's going to give us 0.03, in other words 3%. So that's going to be the interest rate applied each 6 months. Now here's the setup. I've set it up in tabular form. Essentially what we want to do is we want to analyze what's going on with the account every single time we make a deposit. In other words, break the deposits down. We're making 6 of them. Each deposit is $100 in total. But because each of those $100 amounts sits in the account for a different period of time, each one ends up being worth a different amount in the future. So essentially what we have to do is we have to use this formula, but we have to apply it individually to each of the $100 deposits, taking into account how long that particular deposit just sat there in the account collecting interest. So let's start with the first deposit we make. So here's today, we're starting now. Now, why do we not have a payment now? We don't have a payment now because remember, we're making payments at the end of the period. So you can assume this is like January 1st. So January 1st, we're not making a deposit because we're making deposits at the end of each period. So start on January 1st, and then let's see, what would it be? So January, February, March, April, May, June. Okay, so at the end of June, that's when we're going to actually make our first deposit, at the end of that 6-month period. So we put $100 into the account. Okay, so next time we make a deposit will be at the end of December. So $100, then $100 again at the end of December. Then the next year starts, so $100 in June, $100 in December. And then the third year, $100 in June, $100 in December, and that's going to be all 6 deposits that we make. And of course, that's going to total up to be $600. Now what we want to look at is the interest. Different amounts of interest are accrued for each of these individual $100 payments because one sits in the account for a long period of time and one sits in the account for such a length of time that it doesn't actually accrue any interest. So let's start with the first payment of $100. What we want to think about is how long, over how many periods, that $100 accrues interest. So this is at the end of June, okay? I want to think about how many additional interest periods elapse before we get to the end of this investment at the end of 3 years. So here we are in June. Well, starting there at the end of June, we have 1 interest period elapsing to take us to December, then a second period to take us to the next June, a third period to take us to the next December, a fourth period to take us to the following June, and then a fifth period to take us to that final December where we wrap things up. So we actually have a total of 5 interest periods over which we accrue interest. So in other words, this particular $100 actually accrues interest 5 times, because there's going to be 5 times that we calculate interest after this particular amount is deposited in the account. Now you might be asking, why is it not 6? Because we're making deposits every 6 months. We make them 6 times. So why does it not accrue interest 6 times? Well, we are making 6 deposits, but you have to think about what's happening right then. Interest is accrued on money that sat there in the account for a certain length of time. The interest represents how long did the money sit there and how was the interest rate applied in light of that. Well, this particular $100 was deposited on this day. But on that day, how much was already in the account? Well, if that's the beginning of the account, there wasn't actually anything in the account. The account started with a balance of $0. So if we're talking about the 6 months that elapsed between right now until we made that first payment in June, there wasn't actually anything in the account to collect interest on. The balance was $0. So we don't accrue any interest because there wasn't anything in the account. But in terms of when we start accruing interest, we start making interest on this $100 as soon as it's deposited, and then as 6 month periods elapse. There's a total of 5 6-month periods that elapse after we deposit that $100. So there's going to be a total of 5 interest periods over which we calculate interest on this $100. So what we want to know ultimately is, what is this $100, this specific $100 going to be worth after 5 interest periods have elapsed once we get to the end of 3 years? Well, that's when we're going to use the compound interest formula. Now here we're assuming the principal is $100 because all we're interested in is what is happening to this specific individual deposit. So the principal is going to be $100. Our interest rate we know is 0.03, so it's 6% annually, so 3% semi-annually. And then what about our exponent? Well, remember there are a total of 6 periods, but how long did this particular amount sit in the account? How many interest periods did that one take to accrue all of its interest? Well, it sat in the account and accrued interest over 5 interest periods. So our exponent here is actually going to be 5 because that's the total number of periods over which this particular amount accrued interest. So the value of this $100 at the end of 3 years is represented by this particular value. So it's going to be 100 times 1 plus 0.03, which is 1.03, and then it's raised to the 5th power because this particular amount sits in the account for 5 interest periods. So whatever this value is, this represents how much that $100 is going to be worth 5 interest periods in the future once we reinvestigate the value of the account. Now, what about the next one? What about the next $100? Okay, so at the end of December, we make another deposit. So at the end of December, we have that $100 that was already in the account. It's collected some interest. And then we make another $100 deposit. Now this one's not collecting interest yet because we literally deposited on the same day that we added in the interest for what was already in the account. So it doesn't accrue interest until we make that deposit and we start counting again. Now how many interest periods does this one have to accrue interest? We go from December to June, so that's 1 period. June to the following December, which is 2, and then to June, which is 3, and then to December, which is 4. So that particular payment, the next one, the one we make at the end of the year, has 4 interest periods over which to accrue interest. So how much is this $100 going to be worth? Well, again, our principal is $100. It's the $100 representing that individual payment. I is still going to be 0.03. That's based on the structure of the account, not anything specific to how we're making payments here. But what's changed here is the value for N. Before, N was 5 because this $100 had 5 interest periods over which to accrue interest. This one only has 4. So the exponent is going to be 4 in that case. So notice everything is the same except the exponent, because again, this particular amount only sat in the account for 4 interest periods rather than for 5. Now when we evaluate this value, it's going to be smaller. Because the exponent is smaller, the output we get when we evaluate this is also going to be smaller. And you'll notice the pattern. The next one is only going to be in there for 1, 2, 3 periods. The following one is only in there for 1, 2 periods. This next to last one only has 1 interest period, so from June to December when the account ends. And then what about the very last one? Well, think about what's happening. We accrue interest at the end of 6 months and we make deposits at the end of 6 months. So this represents the very last day of December at the very end of the 3rd year. We deposit $100, but how long does it have to sit there and collect interest? Well, as soon as we deposit it, we close the account is essentially what's happening. So it doesn't actually have any time to accrue interest. The number of interest periods that elapse once we make that deposit, well, it's actually 0, because we're accruing interest on the same day and we're also making that deposit on the same day, and then we're closing the account. So this very last deposit of $100 doesn't actually make any interest because it doesn't stay in the account for any additional length of time over which we would accrue interest. So that means when we calculate the value of this one, the exponent is going to be 0. Now an exponent of 0, anything raised to the 0 power, is actually just 1. So if you imagine taking 100 and multiplying it by 1, well, the value you get is 100. So this last deposit of $100 is truly worth $100 because it doesn't have any time to make any interest. But all the previous values, all the previous deposits are going to be worth a little bit more because, again, they had time to accrue interest. So I don't want to go through the whole addition to show you what's going to happen, but I want to show you in general how these values compare. So let's look at the first deposit we made. So the actual deposit was $100, but when we calculate its value, this is going to be the actual value of that $100 at the very end when we reevaluate how much is in the account. So we have 100 times 1.03, and then we're raising that to the 5th power. And then I hit enter, and that's going to be the value. So about $115.93. That's how much this $100 is now worth at the end of 3 years. So how much interest did it earn? Well, we've got the $100. Anything additional added on represents interest. So the first $100 payment made about $15.93 worth of interest. Now, what about the next $100? Remember, this one sat in the account for one fewer interest period. So 100 times 1.03, but now we're raising it to the 4th power because it was only in there for 4 interest periods. And notice it's worth just a little bit less, so $112.55. And again, it's worth less because it didn't have as much time to collect interest. Now, if we were to do that for every single one of these and then total them up, this is what we call the future value. So this is our annuity payment. This is our sequence of equal payments made over equal periods. But if we take what each of those is worth, based on how we're compounding our interest, add all of those values up, that is what we're calling the future value of the annuity. So keep in mind, this sum is going to contain not only the $600 that we got from making deposits, but also the additional amounts that are based on how much interest we earned. And just to show you, at the very end, this is in fact worth $100. 100 times 1.03, and then we're raising that to the 0 power. Well, there you go. That verifies it, $100. Anything to the 0 power is 1, and then 1 times 100 is just going to be 100. But all of the other payments are going to be worth a little bit more, decreasing down to 100. We sum all of those up, and that's the total amount in the account. So hopefully you can see mechanically what's going on. This is what's actually physically going on behind the scenes when we talk about making all these payments specifically into this kind of account that accrues interest. Now, as you can imagine, this would get very, very tedious if we were keeping the account for more than 3 years, or if we were making more frequent payments. So say you kept the account for 20 years and you made a deposit every month. Well, 20 years and then 12 times a year, that would be 240 payments, which means if you were to do it by hand, you'd have to do all of this 240 times, and you'd have to add up 240 values. That would not be a realistic thing to have to do, but technically speaking, that's what's happening. The good news is, rather than having to do this step by step every single time, mathematicians recognized the pattern. They recognized what was happening, and they developed a formula to deal with this, to take care of all these different values following this particular pattern with their exponents, and then find the actual final value, the sum, without having to find these individual values and then just add them up. So you're probably asking the question, why would we go through this if we're just going to use a formula? Well, you're going to be able to use the formula from here on out, but in order to understand what an annuity is, it's important to see it worked out like this at least one time so that we understand the structure of this particular account, what's actually happening, what's going on behind the scenes. That way we have context for what this formula actually represents. So let's look at our formula, summarizing this pattern for how our interest accumulates. Now we're going to introduce one new variable that essentially is going to replace our variable that represents principal. So the reason we have to replace this variable representing principal is because principal is what we think of as starting on day one, and then we just let it sit there. Well, that's not exactly what's happening here. What's happening here is we're making periodic payments. So in place of the variable for principal, we're going to use PMT, which represents our periodic payment. Remember, that's going to be the same value every time. That's part of an annuity. The actual deposit, the payment we're making, has to be the same value every time. So this is going to replace principal, and then FV stands for future value. In other words, our account balance. At the end of all of our deposits, the end of all our interest periods, it's the value of the account. So this is going to be our formula. I and N mean the same things as they always mean. So I is going to be our periodic interest rate. If we take the annual rate, divide it up by how many compounding periods we have per year, that's going to be our value for I. Notice we use that value twice in the formula. And then N is going to be the total number of periods that we have to accrue interest. So it's the total number of payments, and it's also the total number of interest periods. So let's determine what the value of that actual account was, the one we just looked at where we're adding in those $100 every 6 months, and then we have 6% annual interest on the account. What's the future value of that annuity? And then it's also helpful to think about the question, how much of that is interest? How much of that actually represents interest versus the amounts representative of our actual deposits? So every time we look at an annuity, we're going to start by looking at two things. Number one, we want to determine the value for I. What is our rate per period going to be? Start by determining that. And then also we want to determine the value for N. How many times do we make deposits? How many times do we accrue interest? We need to know what that's going to be. Then we can just plug everything into our formula and we can go for there. So the rate per period is going to be 6% divided by 2, which is 0.03, so we already determined that. And then the total number of periods, well, it's twice a year for 3 years, so that's going to be a total of 6. Now remember, when we looked at the table, it was a little bit different. When we looked at the table, we didn't actually have an exponent of 6 anywhere. We had exponents decreasing from 5 to 0, but that's because we were focused on applying the interest formula to one payment at a time based on how long each of those payments sat there in that account and accrued interest. This is a little bit different. Here, we're talking big picture. How long are we keeping the account? How many payments are we making in total? And how many times are we accruing interest from start to finish? And so in this case, it's going to be a total of 6 periods. So now all I have to do is plug those values into my formula. So our payment is going to be $100. I, we determined, is going to be 0.03, so 1 plus 0.03. We know N is going to be 6. And then notice in our numerator, 1 plus I to the N, that basically looks like our compound interest formula. We're going to subtract 1 from that. And then all of that is going to be divided by 0.03. Okay, now as with the compound interest formulas, there's a variety of ways you can simplify something like this. So I want to show you a few different ways you can simplify something like this, either all in one line. You can do it all in one step if you want. You can follow order of operations. You can break it down and do a few things at a time and then add on as you go. You have a lot of options here. So let's do it all in one line first, and then I'll show you how you break this down and do it one step at a time, just based on order of operations. Okay, so all in one line, we need to start with our 100. And notice 100 is multiplied by all of this. So I'm going to type my 100, but because the 100 is out front and it's now multiplied by this ratio, I'm going to put parentheses and then I'm going to type the ratio in. Now, there are a lot of layers for what's happening with this ratio. So this set of parentheses encloses the entire fraction. Okay. Now, we also have to have parentheses around our numerator so that the whole numerator is divided by the denominator. But within that, we also have to have parentheses that are actually part of the formula. So one set of parentheses for the fraction, another set of parentheses to separate the numerator from the denominator, and then a third set of parentheses to take care of the ones that are actually part of the formula. What you're going to have to be careful about here, if you want to do it in one line, is you have to make sure once you open a set of parentheses, you close it. If you don't close it, it will change the formula. It will change the structure of what you're trying to type. So we have our parentheses for the fraction, parentheses for the numerator, and then parentheses for the actual parentheses. So 1 plus 0.03. Now close the parentheses. Those are the actual ones written down. We're taking that value and we're raising that to the 6th power. Okay, now I'm going to arrow out. If I have one that's formatted as an exponent, I'm going to arrow out. Remember, you may just have the up arrow drawn. If so, then you just keep typing after that. Okay, so out of the exponent. Now from that, we're subtracting 1. Now that's the entire numerator. So now I'm going to close the parentheses representing that numerator. So I've closed the parentheses that were actually in the formula. I've closed the parentheses representing the numerator. So from that numerator, I'm now dividing by 0.03. And then that's the end of the fraction. So I'm going to close my last set of parentheses. So you do want to verify. You have 3 parentheses that open. You have 3 that close. So 3 that open, and then 1, 2, 3 to close. And that is going to be the whole line. That's going to be everything you want to type in. So we hit enter, and there we go. So 2 decimal places, cents, that's going to be $646.84. Now, what about interest? We also asked the question, how much of that was interest? Well, remember, interest is always defined as the difference between your account balance and the amount of principal in your account. The biggest difference here, though, is principal is not a set amount that we started with. Principal here is represented as a sequence of payments, a sequence of $100 deposits in the account. But how many of these $100 deposits did we make? Well, we made a total of 6 of them, so 2 a year for 3 years. So our principal is actually going to be the payment we make multiplied by how many times we made that payment. So it's going to be 6 times 100, which is a total of $600, which was the total that we deposited in the account. So the amount of interest is going to be our balance minus the total of our payments, which is going to be 6 times 100. And if we subtract those 2, the difference is going to be $46.84. So $600 of this amount came from us, and then $46.84 was represented as interest. Okay, now before we move on to the next one, I want to show you how you would do this particular problem, evaluate this particular formula without having to use all those parentheses, just going one step at a time, evaluating one operation at a time. And you might not have wanted to do that with the plain old compound interest formula. Here you may want to, particularly if that issue with all of those parentheses makes you a little bit nervous. So just like before, we want to go through this formula and we want to follow the order of operations and determine what order we'd have to do things in. Well, you can think of the numerator and denominator as kind of being separated structurally like parentheses separate things. So you can't actually divide until the whole numerator is simplified and the whole denominator is simplified. So let's focus on the numerator. Well, there's a few things going on in the numerator, but we clearly have a set of parentheses. So that means that's going to be the absolute first thing that we simplify. So I'm going to do one operation at a time. In this case, the starting operation is going to be that addition in parentheses. So 1 plus 0.03. Okay, so that's now going to be our value in parentheses. Now that value is being raised to the 6th power. So immediately I'm going to take that most recent result, I'm going to raise it to the 6th power. Now anytime you take a decimal and raise it to an exponent, typically that's where numbers start to get bad. We don't want to round though. We're going to continue to build off of this in the calculator so that we only have to round at the end. So from that we're subtracting 1, so minus 1. That's now our whole numerator. That's what we're now dividing by 0.03. So take that numerator, divide it by 0.03. Okay, so that's now the value of our fraction. Notice what we have here though. We have 6 and then we have a fraction. This is what's being multiplied by our payment of 100. So 6 times 100 actually represents the number of payments we're making, right? And then the decimal times 100, that's going to represent the interest. So we multiply this by 100, and that's going to give us the balance. And again, it's the same number, so $646.84. I personally prefer to do it this way, just because I know I'm not going to have to worry about missing a set of parentheses. If I just add on one operation at a time, then I'm not going to run the risk of missing a set of parentheses and evaluating a formula incorrectly. So I'm going to continue doing it this way for the duration of the video. I would encourage you to try both ways, see which one you seem to prefer. If you feel confident that you can do all the parentheses correctly, then by all means evaluate it that way. That's perfectly fine. Okay, let's look at another one. What is the value of an annuity at the end of 20 years if $500 is deposited each quarter into an account earning 8.5% interest compounded quarterly? And then we want to know how much of this value is interest. Okay, now we know it's an annuity. It's growing in value, so we're looking for its future value. That's why we're going to use the future value formula. Now, what is our payment? That's usually easy to spot. In this case, we're depositing $500 each quarter. So it's the same amount, and the amount is going to be $500. So that's going to be our value for payment. Now, notice we're depositing each quarter, and we're also compounding quarterly. Again, those values have to be the same. So every 3 months, it's important that those match up. So what we're assuming is that every time we make a deposit, we're also calculating interest at the same time based on whatever's already in the account. Okay, so what's our rate per period going to be then? Well, we have 8.5% interest annually, but we're calculating interest every quarter, in other words, 4 times a year. So 0.085 is our value for R, and then we're dividing that by 4 because we're compounding quarterly. So let's see what that is going to be. So 0.085 divided by 4, and that's going to be our value. Do not round this. You see that? You want to round it. This is an exact value. Do not round it. You have to use that whole thing. More than likely, if you cut it off, your final answer is going to be wrong. And when the homework system tells you your answer is wrong, it's wrong for a reason, because you rounded too early. Use this whole value. So that's going to be our value for I. So about 2.1% interest per period for a total of 8.5% interest across the year. Now we also need to know how many interest periods and how many payments there are going to be. Well, we're keeping the account for 20 years and we're making this deposit every quarter. In other words, 4 times a year. So 4 times a year for 20 years is going to give us a total of 80 deposits and 80 interest payments. So that is going to be our value for N. So using our formula, payment is going to be 500, and then we have 1 plus our rate per period, which is 0.02125. Notice again, I did not round it. That's going to be raised to the 80th power minus 1, part of the formula. And then again, we're dividing by that particular rate per period. So let's see what this is going to be worth. Now again, I'm going to go step by step, one operation at a time. So that's going to be in parentheses in the numerator first. So 1 plus 0.02125. Okay, there's everything in parentheses. Now we're raising that to the 80th power because we have 80 periods. Now, here is where if you wanted to write something down, you'd have to round, but because we're continuing everything in the calculator, we're going to work off of that total, and then from that, we're directly going to subtract 1. Okay, so that is now our entire numerator. Now, when we divide, normally a number gets smaller, but notice the number we're dividing by is a number that's less than 1. If you divide by something less than 1, then the output from that division, the quotient, is going to be larger. So let's see what actually happens to this number. So we're dividing by 0.02125. And notice we go from about 4.4 to about 206. Again, that's the result of dividing by something that is less than 1. So that gives us the whole fraction. That's going to be the multiplier for our payments. So that tells us how our payments increase in order to give us our future value. So multiply that by 500. That is going to be the value of the account. So $102,995.67. Now, why is it worth so much? We go from $500 to this value. Well, remember, that's not quite what's happening. We're making $500 deposits 4 times a year over 20 years. So how much actually represents interest and how much actually represents our deposits into the account? That's the next question we want to answer. Well, let's think about how much money we deposited. So we made 80 deposits in total, and each deposit was worth $500. So we made a total of $40,000 in deposits. Now this number is starting to look a little bit more realistic, right? Well, this is the value of the account, and then if we subtract how much is represented as our money we deposited in the account, the difference is going to give us interest, and in this case, that's going to be $62,995.67. So what I want you to notice here, compare these two numbers. Remember, this was 40,000. This is the amount of interest. So more money in that account was actually interest than was deposited money. That is the benefit of having an interest-bearing account. The fact that we put money in the account regularly and we just let it sit there and collect dust means it grows quite a bit. And the interest represents essentially most of the money. It represents more than half of the money that we have in the account. That's why retirement accounts grow so large. So if you make periodic payments, deposits into a retirement account, how do you end up with so much money when you're ready to retire? Or hopefully you end up with a lot of money. You do because you start making payments early and you have a lot of time to collect interest. So even if the interest rate is not extremely high, the fact that you're letting it sit there for so long, in this case over 80 periods, means you end up making a lot of interest, potentially more than you actually deposited in the account from your own money. Okay, let's look at another kind of situation. So when we looked at our compound interest and simple interest formulas, we also talked about the kind of problems where we wanted to meet a goal in the future, making a certain amount of money, but we needed to know what kind of deposit do we have to make today, in other words, what is the principal, in order to meet this goal in the future. So what might that look like if we're talking about an annuity payment and the future value of a sequence of annuities? Well, here's what it might look like. What we want to know is what annuity payment, what's the actual payment that should be made in order to accumulate $5,000 given a rate per period of 1% over 15 periods. Okay, well, immediately the question says what annuity payment, what payment? So PMT, payment, that's going to be our variable here. That's what we're trying to determine. Now the goal is to accumulate a total of $5,000. So that's the future value we want for this account. That's how much we want to be in the account in the future. Now we've been told that this particular account has a rate per period of 1%, and we're going to keep this account, we're going to make deposits for 15 periods. Now we've been given a little bit different information here than we were given before. So before, we were given an actual interest rate, we were told how we're compounding, and then we were told how many years we want to keep the account. And we had to find the rate per period, and we had to find the number of periods. Well, here, this is a little bit different. We've been told what the rate per period is, and we've been told the total number of periods. So some of the work has been done for us. So if we've already been given the rate per period of 1%, that's going to be our 0.01, okay? So that's gonna be our value for I. And then 15 periods means N is going to be 15. Okay, so since we already have those values, we don't have to do anything to them. If you had information given like it was given in the last two problems, you find I and you find N based on that information. So this is going to be I, this is going to be N. We're going to plug them into our formula. But again, keep in mind what's unknown, what's variable, and what we actually know. Here, we know the future value that we want. What we don't know is the payment. So we have $5,000 as our future value. Payment is variable, it's what we don't know. And then we have the rest of it given. So 1 plus 0.01 raised to the 15th power, there's our I, there's our N, minus 1, divided again by our rate per period, 0.01. Now, just like the problems where we looked at simple interest, we looked at compound interest, and we wanted to determine a particular amount of principal, what we were multiplying by the principal was actually just a fixed number. It represented one constant number. And we were able to just divide it out since it was multiplied by the principal, move it over to the other side, and then solve for principal in essentially one step. The same thing is true here. So we have this particular value. Notice there's a lot going on here, but it's really just one number. Everything in here is given, there's nothing variable. So it's just payment multiplied by this number. So we can start by evaluating what that number actually is. Simplify all of that in your calculator. And again, I'm going to follow one step at a time, order of operations, just so I don't have to use any parentheses. So we'll start inside parentheses. So 1 plus 0.01. Now we're raising that to the 15th power. And then we're subtracting 1 from that. And then we're dividing by 0.01. Now I've approximated it on the actual sheet, but as with any problem, you want to keep that running total in your calculator and you want to build off of the number in your calculator. So this is now the number that's multiplied by PMT. Well, if we want to solve for PMT, we want to isolate it, and something's multiplied by it. We undo that multiplication by dividing. So we have to divide both sides of our formula by this particular number, which again is this number, the number we now have in the calculator. So we divide it on the right-hand side, and that's going to isolate PMT. We also have to balance the equation by dividing it on the left-hand side. Now be careful how you do this. It's not going to be this number divided by 5,000. That's reversed. It's going to be 5,000 divided by that number. So we're going to have to use the ANS button in the calculator. So we're taking 5,000 and then we're dividing by this previous answer that we got that was just built upon in order to generate the value of that fraction. But remember, we don't have to type it again. Go to your negative button at the bottom. Right above it in blue it says ANS. So second and negative pulls up that answer from the previous line, and that's going to be the division we want to do. So there we go. That's going to be the value. So $310.62. That's going to be the payment we need to make. Does that make sense? Well, if you ended up with a payment that was more than $5,000, that would not make sense. If the goal is to get to $5,000, why would you need to make a payment of more than $5,000? Here, this makes sense. $310.62. We're making this payment 15 times in order to get to an account balance of $5,000. So if we're making this payment 15 times, what does that actually represent? So $310.62, and we're making that payment 15 times. This is going to be the total amount for our payments, so $4,659.30. Well, you might be looking at that and saying, that doesn't get to $5,000, that doesn't cover it. We wanted to get to $5,000, we only got to $4,660. Why is that? Well, remember, we're making these payments understanding that we accrue interest. So this is the money that we have to supply each period. And in order to get from the total amount of our deposits to $5,000, that is what the interest is going to do for us. So the rest of the money that we would need to meet our goal of having $5,000 is going to come from the interest we accumulate. The first time we deposit this amount, we make a significant amount of interest. The last time we make this deposit in the account, we don't actually make any interest on it. But the total of all of these deposits, plus whatever interest we earn over our 15 periods, that's going to get us to this goal of $5,000 in this account. Okay, so that's what it'll look like if we want to solve for the payment. Now, one thing I want to emphasize now, we're going to look at an example, an actual applied example, but sort of in preparation for what we're going to look at in the next section. We're also going to look at annuities there, but it's going to be a slightly different situation. How do you know which situation you fall under? Well, when we're talking about future value specifically, which is what we're talking about here, future value applies in situations where our account balance is growing. We're attempting to grow the account. We're making an investment in the account, same investment over equal periods of time, with the goal of increasing the balance in the account. Now, we're also going to look at situations where the balance is decreasing, thinking of paying off something like a loan. You make equal payments over equal periods of time, but the balance of the account is going down. You're paying off principal and you're paying off interest in order to get down to a balance of zero. So anytime we're looking at a problem where the account balance is growing over time, that's going to be a future value problem. If we're looking at a situation where the payments we're making are decreasing the value of the account in order to take it down to zero, that's going to be a different kind of problem, and we're going to have to use a different kind of formula. So let's look at a couple different situations where we would use this future value formula and we would structure some type of annuity payment. So what we're going to talk about here is what we call a sinking fund. So a sinking fund is just an account that we establish for accumulating funds in order to meet future debts or obligations. And in order to meet this goal of covering our debt in the future, we may establish our fund, our account, as an ordinary annuity. In other words, we make periodic payments anticipating this particular thing we're going to have to pay off in the future. So suppose you have a piece of equipment. This is the situation we're going to look at. We know we're going to have to replace an expensive piece of equipment that costs $800,000 in 5 years. What we currently have is not going to work for us in 5 years, and we're planning for the possibility of having to replace it in the future. So rather than having to come up with $800,000 at one time, we want to put a little bit into an account over 5 years so that by the time we have to replace this item, we'll have all the money we need to replace it. That is the idea of a sinking fund. We're putting money in the account now, we're collecting interest on this money in order to meet this particular obligation that we expect to have in the future. Okay, so to have this money available, this $800,000 available in 5 years, we're establishing this sinking fund by making equal monthly payments into an account that pays 6% interest, and that interest is compounded monthly. So we're going to break this down into a couple of different layers. First thing we want to know is how much should each payment be? What do we need to plan to deposit each month so that in 5 years we'll have enough money in the account to cover $800,000? Well, we're not going to have to make a total of $800,000 in payments because remember, interest is going to do some of the work for us. We make a certain amount of deposits that total a certain amount, and then the rest of it, the rest of meeting that $800,000 goal, is going to come from the interest that we accrue on this account. So the goal is to grow this particular account, so we're looking at a future value problem. Now our question is how much each payment should be. So we're looking at the same kind of problem we were looking at above. We know the future value we want is going to be $800,000. We want to have that much in the account. But the question is, what kind of deposits do we need to make in order to get to an account balance of $800,000? So we're going to use our future value formula, but we're going to use it the same way we used it above. where PMT is going to be our variable. So we want to start with I, and we want to start with N. So I, remember that's going to be our annual rate, 6.6%, but we're compounding monthly. So we're dividing that rate into 12 parts. So let's see what happens when we do that there. So 0.066, we're dividing by 12, and that's going to be our interest rate. So 0.0055, that's our rate per period. Now, how many periods do we have? Well, we want to have money in 5 years, and we're making monthly payments and accruing monthly interest. So 12 times a year for 5 years, that's going to be a total of 60 payments and then 60 interest periods. So we know everything we need to know in order to use our formula. Now we just need to plug in our numbers. So the future value we want is going to be 800,000. Payment is our variable. And then 1 plus 0.0055. We're raising it to the 60th power because that's the total number of periods. Subtracting 1 and then divide by I again. Now, just like with the previous one, notice everything multiplied by payment is constant. So if we simplify that value, we can then divide that out, and that's going to isolate PMT. So one step at a time, we have 1 plus 0.0055. So that's in parentheses. That's now raised to the 60th power. From that, we're subtracting 1, and then we're dividing by 0.0055. That is now the value that is multiplied by PMT. So that's also going to be the value that we have to divide out in order to isolate PMT. So I divide it on the right hand, that isolates PMT. I have to divide it on the left-hand side in order to balance the equation. So $800,000 divided by this particular value, which I can get from second negative, which gives me A and S. Okay, and there we go. That's going to be the amount we need to pay. So $11,290.42. Okay, so what happens when we make that many payments? We'll answer the next question in just a moment, but let's think about what that actually means. So every single month for 5 years, I'm putting $11,290.42 into my account. So I'm doing that 12 times a year, and I'm doing that for 5 years. So that's going to be the total amount I deposit in the account from my own money. So $677,425.20. Now again, that doesn't take us all the way to 800,000 because the rest of the money, in order to meet that goal, is going to come from the interest we accrue on the account. So now let's take it one step further. We want to answer one last question. How much interest is earned during the last year? In other words, the 5th year. This is actually a fairly complicated question. Normally we would say, well, okay, if this is the amount that we put in the account, we know we're going to have a total of 800,000. The rest of it is going to come from interest. So if I were to think of 800,000 as being where I end, this is how much I deposited myself. Well, that particular amount represents interest. It's interest accrued over 5 years. So if we were to divide that into 5 parts, well, that should be the amount of interest per year, right? That would make sense. Unfortunately, it's not that simple. This is the total amount of interest we accrue over the course of 5 years, but it does not represent one particular amount divided into or multiplied by 5. It doesn't represent this particular amount multiplied by 5. What's the problem with that kind of logic? Well, the problem is compound interest doesn't work that way. Money that's in the account early on accrues more interest than money that's in the account later on. So if you think about what's happening to the account over 5 years, in the first year, you make 12 payments, okay? So you accrue a certain amount of interest. Now, at the end of the second year, you've made 12 more payments. There's more money in the account. So that means when you accrue interest for that year, you actually accrue more interest than you did in the first year because there's more money in the account. So each year we end up making a little bit more interest than we did during the previous year because we have more money in the account that's actually collecting interest. So it's not as simple as just saying this is the total amount of interest. It's 5 years, was divided up over 5, getting tongue-tied. It's not that simple, unfortunately, because the amount of interest accrued per year is different for every single year. So what are we actually asking when we're asking this question, how much interest is earned during the last year, in other words, the 5th year? Well, what we need to know is what sort of changes were made as we went from the end of the 4th year, which was our next to last year, to the end of the 5th year. What happened in that 1 year span to take us from where we were at the end of the 4th year to where we are at the end of the 5th year when we're supposed to meet our $800,000 goal? So it's multi-layered. We have to answer all of those kind of questions. Where we need to start, though, is we need to think about what's in the account after 4 years specifically. Once 4 years have ended, where are we in order to determine what happens in the 5th year? Well, what's happened after 4 years? Well, we've made 4 years worth of these payments. We know how we accrue interest. Now, what's going to change is the value for N that we use in the formula. It's not going to be 60. Why is that? Well, we haven't made 60 payments after 4 years. How many have we made? Well, if we're making 12 payments a year, and now we're only looking at the first 4 years, that means we've made 48 payments so far once we get to the end of the 4th year. So if we're looking at just what happens from today to the end of the 4th year, we're only looking at a total of 48 payments so far. So the value in the account after 4 years, the future value after 4 years, is going to be our payment. We know that's the payment we need to make, multiplied based on that particular value of N, in this case 48, representing 48 payments over 4 years. So let's see what this value is going to be. That's going to be the value in the account after 4 years specifically. So in the numerator, 1 plus 0.0055. Now we're raising that to the 48th power for 4 years, 12 payments per year, okay? From that, we're subtracting 1, and then we're dividing by that value for I, so divided by 0.0055. Okay, so that is now the number multiplied by our payment, so times $11,290.42. Okay, so that's going to be $618,277.04. That is how much is in the account at the end of 4 years. Well, at the end of the 5th year, we know we're going to get to $800,000. It may be a little bit more, but in theory, we're just going to base it on meeting that exact goal of $800,000. So what happened between the 4th year and the 5th year? Well, we made about $618,000 up to that point. How much more did we accrue in the 5th year? Well, we get to that goal of $800,000 based on our payment plan. Let's see, let me clear all this. So $800,000 minus how much we've already paid and how much we've accrued. So $618,277.04, which means $181,722.96 were added to the account in the 5th year. That's the growth from the 4th year to the end of the 5th year. Now, keep in mind, this represents 2 components. It represents all the payments we made in the 5th year, but it also necessarily represents all of the interest we accrued in the 5th year. So some of that is payments, some of that is interest. We can actually determine what the payments are, though, because we know what our payment schedule is. We made the same payment every single month for a total of 5 years. Well, if we're just looking at 1 year, it's that particular payment value we made, but now we're only looking at 12 of those payments because we're just looking at what happened in that 1 year, in that last year. So how much of this amount came from our deposits, from our payments, and how much of it came from interest? Well, if we're looking at our payments, each payment we make is $11,200 or $290.42. And from the end of year 4 to the end of year 5, we've made 12 of those payments. So that's the total deposit that we made in that particular year. As it turns out, that's the total deposit we make in every year, because we're making the same kind of payment the same number of times every year. This is always going to be what we deposit. What changes is interest. So payments we put in the account are going to be the same. The interest is what's changing from year to year. So this is how much we contributed to that growth. So that's not all of it though, right? So 135 to 181, what accounts for the difference? Well, the difference between the two is the interest. So if we know that difference between the two, if this is our growth for 1 year and this is how much of that growth came from our deposits, then the difference between the two represents the interest we earned in the last year, which is what we're attempting to find. So $181,722.96, the total amount over the 5th year, minus everything that we put in the account, that is going to be the amount of interest we accrued. So $46,237.92. And as it turns out, that will be the highest amount of interest we earn for a year. Because we have more money in the account in that 4th to 5th year than we did in any of the previous years, we will earn the most amount of interest in that last year, because again, we have the most amount of money, or we have the highest amount of money in the account. So that's going to be the interest during the 5th year. So let's just recap. I want to go through the procedure for this one just real quick. Since there's a lot of layers here, let's think through what happened. So we determined our payment based on meeting the goal of $800,000 and based on our particular rate per period and the fact that we were going to make 60 payments and accrue interest 60 times. So we determined that payment to be about $11,300. And then the question was, how much interest is accrued during the last year? And again, we determined you can't just make this payment 60 times, subtract it from the goal of 800,000 and divide it up over the 5 years. Unfortunately, it's not that simple because we make different amounts of interest each year. Early on, we're making less interest. Near the end, we're making more interest because there's more money in the account. So essentially what we're doing is we're generating everything that happens between the 4th year and the 5th year. So we determined where the account stood after 4 years, how much is there. In other words, if we make our particular payment, but we've only made it 48 times so far, we've only made that payment for 4 years, this is how much is in our account versus the 800,000 that we need. So the 800,000 came from the additional growth in the 5th year. So 800,000 minus where we were at the end of year 4. That's going to be how much we made in year 5. We made 12 payments across the year based on our individual annuity payment. That payment's always the same every single month. So we made 12 of those payments for a total of about $135,500. If this was our total growth for the year, and this was how much we put in the account, then the difference between the two represents the interest we earned. So that's going to give you a sense of how you break down a problem. The biggest thing, again, with compound interest is the amount of interest changes. That's sort of a hallmark of compound interest. When we're talking about simple interest, in general, the interest payment is always the same. When we're talking about interest is compounded, because we're earning interest on our interest, essentially is what's happening, we end up earning more interest the longer we let the money sit in the account. Now let's look at another situation where we have to use this annuity formula, but maybe we have to use it in a slightly non-traditional, predictable kind of way. Okay, so here's an example. An employee deposits $2,000 annually into a Roth IRA. In other words, the interest is tax-free, and this account earns 6.85% interest that's compounded annually. So annual deposits and then interest is compounded annually. Those things match for a reason. Now, due to a change in employment, these deposits stop after 10 years, but the account continues to earn interest in the same way until she retires 25 years after her last deposit. What we want to know is how much is in the account when she retires. Now, this is similar to that question we were asked about interest. How much interest was accrued in the last year, in other words, in the 5th year. Essentially what we have to do here is we have to break this account down into 2 pieces, and we have to analyze what's happening in this account in 2 pieces. Now, why is that? We have to think about what's physically happening. Okay, so we have an employee, she's making annuity payments, $2,000 a year, but she's only making these payments for 10 years. Once she gets to the end of 10 years, she stops working, which means she stops making deposits into this particular account. But she's keeping the account, and she keeps it for an additional 25 years. So for 10 years, she's making payments, and then for the next 25 years, she's just letting the money sit in the bank, and she's just accruing interest on it without adding any of her own money to the account. So for the first 10 years, we're looking at an annuity. Once we get to the end of 10 years, we have a particular balance. That balance continues to accrue interest. So for the next 25 years after that, we're actually just looking at a standard compound interest problem. As long as we're not adding our own money to the account, but we're accruing interest, then it's just a basic compound interest problem. So we have to break this problem up into those 2 pieces based on what happens for that first 10 years, and then based on what continues to happen for the next 25 years. So let's look at the annuity component first. So we're making a $2,000 payment every year, so 1 time a year, and then we're also accruing interest 1 time a year. So our rate per period, actually nothing special happens here. So the interest rate is 6.85%, and it's compounded annually. Annually just means 1 time a year. So we only have 1 interest payment a year, so we divide it by 1, which does nothing, right? Well, how many payments are being made? How many interest periods do we have? If it's 10 years and we only make 1 payment and only get interest 1 time a year, then it's just going to be a total of 10 payments and 10 interest periods. So that's going to be our value for N. So the value of this annuity, her payments plus the interest she earns, it's going to be the payment of $2,000, 1 plus our rate per period, raised to the 10th power minus 1, divided again by that same number. So let's see what that one is going to be. So start in parentheses, 1 plus 0.0685. Now we're raising that to the 10th power. From that, we're subtracting 1. And then we're dividing by 0.0685. So 13.72 roughly. So that number is then multiplied by that $2,000 payment. So 10 comes from those actual payments, and then the other 3 point whatever comes from the amount of interest we're earning. So multiply that by 2,000, and that's going to be the amount in the account. So $27,437.89. Some of that comes from her payments, some of it comes from interest. How much is which? Well, we make a $2,000 payment once a year for 10 years, so that's going to be a total of $20,000 that this particular person deposits. But if we make it to 27 and a little bit, then that means the rest of that, anything beyond $20,000, that's going to be the amount of interest that was earned. Now, what's happened? She's made all of those payments, she's made 10 payments, and the deposits stop. But again, she's keeping the account. Nothing in terms of the account changes. It's just she's not adding any of her own money to it. So what we can now do is we can kind of think of this as the principal for our next calculation. This is where we are. This is how much money is in the account once we look at the next 25 years. So if we think of this as the principal for the account at the end of 10 years for the next 25 years, then we can just use the compound interest formula and use this as our value for P. Now, I does not change, but N does. Why does N change? Well, we're looking at a different length of time. We talked about making payments for 10 years, but now we're just letting the money sit and collect dust for 25 years. So the number of additional periods that we follow is going to be 25. We're still only making interest once a year, but now we're looking at a total of 25 years from where we start once the deposits stop to where we end once we've accrued all the interest that we're going to earn. So P, that's where we start at the end of 10 years, at the beginning of the next 25. I has not changed, and then N is going to be 25 since we have 25 years to go, 25 interest payments to accrue. So that is going to be the final value for the account. Now this one we can probably just type in one line. So $27,437.89, the principal, the new principal based on where the annuity payments stopped. And then we're multiplying by 1 plus 0.0685. Make sure to close your parentheses. And then we're raising that to the 25th power. Now, just as before, if you want to do one operation at a time, you don't want to type it all in one line, perfectly fine, that's up to you. And there we go, there's our value. So $143,785.10. Look at how much change there was. We went from about $27,500 to close to $144,000. And what's amazing about this is if you think about what was actually happening when we looked at the annuity, she was having to add her own money to the account. She added a total of $20,000 of her own money and made about $7,500 in interest, right? Whereas once she just had this money in the account and just let it sit, she went all the way from $27,000 to close to $144,000. But what happened between these two numbers? She didn't actually add anything to the account. She just let the money sit there and collect dust. But because there's so much money in the account now, there's a lot to collect interest on. So over the first year, she collects interest on this amount. Well, that amount is then added back in. So the next time they calculate interest, she's making interest not only on this original amount in the account, but also on the interest she'd already earned. So over the course of 25 years, this particular account grows significantly. So one takeaway from that, one thing to think about, does it make more sense or is it more valuable to make periodic payments or to take the same total amount and dump it into the account on day one? Well, the answer is the second one. It's always going to make you more money if you deposit everything now rather than making periodic payments over time. That's because all of that money has more time to accrue interest. If you're looking at keeping an account for 20 years, well, you can make payments over 20 years, but only the first payment that you make will have the entire time to accrue interest. Every successive payment is going to have less time to make interest on it. Whereas if you just dump all the money in on day one, all of the money collects interest for the whole time. So you end up making a lot more interest overall. Now that requires having all that money up front, which most people don't. So most people plan for retirement by making periodic payments because that's what's realistic to do. But if for some reason, say you won the lottery, something like that, and you want to plan for retirement, rather than making periodic payments into your account, if you were to just set aside a large amount of money, put all of that money into the account, you have more time to accrue interest, you have more money that you're accruing interest on, and so it ends up being worth more in the long run. So just to sum up what we've looked at, we've talked about an annuity. Think equal payments, it's always the same amount, and then it's made at equal periodic points. So we always make the same payment, we make it at the same time across the year. And again, future value, these are going to be situations where we're adding to the account and the interest is increasing the account. So what we're going to look at in the next video is situations where we're making annuity payments, we're making equal payments, we're making them at the same time, but the goal is not to grow the account. The goal is to pay off an account, something like a loan. We're going to talk about what that looks like. We're going to investigate how that looks from a mechanical standpoint, and then we're going to look at the formula that takes care of that for us.